by applying the current or voltage to the gate or base, we control the current flow between other two terminals. What is that other two terminals? Because we are already using one terminal, gate or base. So other two terminals, maybe it can be drain and source, or it can be emitter and collector. So different names are used for the devices based on the device physics. Okay, so basic principle is the same, right? I am applying voltage here and I control the current flow. Then why I call this as a BJT, and why this is MOSFET, and why this is IGBT, instead of I just use one device for everything. So it's really depending upon the device physics, how the device structure is built, how you fabricate this device. So it means how we combine N type and P type semiconductors together to make the conduction of the current. So, you know, P type semiconductor, N type semiconductor, this also you have studied in your electronics course. In P type semiconductor, we are adding P type impurities, and N type we are adding N type impurities. So by changing the doping level, so by adding impurities into the pure semiconductor, the process is called doping process. So by changing the doping level, it means you are adding impurities to the pure semiconductor in different amount. We can change the electron flow. What is electron flow? That is the current. So based on the doping, we can classify into normal doping. There is a P semiconductor or N semiconductor, N type semiconductor, or it's a heavy doping. So we can call that as a P plus, N plus, means heavy doping. It has a lot of holes and it has a lot of electrons. And the third type is called light doping. So normal doping, heavy doping, light doping. How can we indicate them? So normal doping is just P, N. Heavy doping is called P plus, N plus. Light doping is called P minus, N minus. So based on these doping levels, the conduction will be different in each device. And also what kind of layers you are using and where you are making the well and so on. You need more or less force to move electrons or to break the depletion layers between P-type and N-type semiconductors. So based on this doping level, so you need to give the force because the depletion layer will vary. I will explain again one more time here. Here you can see the working logic of IGBT. IGBT is insulated gate bipolar transistor. We had seen the symbol just before. So this is the device structure. So here you can see this is the device structure of IGBT, or this is how IGBT is designed by the manufacturer. So what we are having here, we have a metal plate. This is called the metallization. After that, we have the P plus region. P plus region means what? So please remember P plus, heavy doping. So we have a heavy doping of holes. So here holes are majorities, so many holes here. So you can see like holes are too close to each other, maybe million, billion holes, heavy doping. And then we have another region, it's N minus region. So what is N minus? Again, please try to remember, N minus is a light doping. Okay, we have N minus region. So we have completely N minus region. Into this N minus region, I am going to diffuse another P region. P is what? P is just a normal doping. So here we have a P type region in both sides. I diffused. So inside this P region, again, I am making two small N plus region. So I can call this as N plus region or N plus well. Well means what? We have a well, some of us we have in our home to have a water. So here we have N plus well. So N plus means what? Again, you please remember, this is heavy doping. N plus means we are doping. It has too many electrons. Now I am just putting the silicon dioxide, SiO2 in the top, and putting some metal plate and taking the terminals. So now I have the emitter, I have the collector, I have the gate. Only three terminals names actually. So we are just having one common emitter because I will show you that in a while. So now we have emitter, gate, collector, three terminals in this IGBT. And here, this region is called body region, and this N minus region is called a drift layer. And this green one, P plus region, it's called injection layer. So we have injection layer, drift layer, and body region. The name is not important here. So the most important thing is here, the three terminals, and these are the structure. This is the structure of the device. And here, the most important thing is we have two junctions, major junctions, that is called J1 and J2. J2 is the meeting point of P type region and N minus type region. J1 is the meeting point of N minus and P plus. So this junction meeting point we can also call as a junction. So junction 1, junction 2. So now what's happening? So now I apply the voltage between, here you can see, between this emitter and this collector. There will be no current flow. Maybe I change the color of my pen. So now I apply the gate voltage. This is called VCC. We are applying between emitter and collector. Now I apply the VG, that is the gate voltage. Gate voltage. So I'm giving positive to this gate and negative to this with respect to this emitter. So like this, negative, and here is the positive. And now what's happening? Without giving the gate voltage, if I just only apply this VCC, there will be no current flow here. So when I apply this one, what's happening? So whenever this VG is greater than VG threshold, that is the threshold voltage of this device. Typically, it's 0.7 volt for silicon based semiconductors. So whenever this VG is more than 0.7 volt, then N channel is formed in the P region. N channel means there is the electrons. And this N channel short circuits this N minus region with N plus emitter region. We have this N minus region and we have N plus region. So because of this N channel created by this gate voltage, it's short circuiting this N plus into this N minus. So you can see here the channel got created. So now an electron movement in the channel, in the N channel, in turn causes substantial hole injection from P plus substrate layer into an epitaxial N minus layer. So because of this short circuit, here we already have in this P plus, we have a lot of holes. Remember, is a heavily doped one. So the depletion layer width is much smaller here. So that can easily broken and the current flow starts. So now the channel got created. So we are step by step, we are doing this. So we are applying the voltage to this gate and we are creating the electrons here. Then it short circuit this P and this N minus. Once after that, then the current flow already it's very heavy here. the electric field is very heavy, and here the depletion region is very weak because of this P plus, so it can easily break this one, and then the current flow starts from, because this P plus is connected to this collector terminal. So now the current flow starts from this collector to this emitter. That is what we want. So we are achieving this current flow by applying this gate voltage. So thus in turn establishes forward current flow as shown in figure. Yes, so that is how each device is working. So we had seen bipolar transistor, MOSFET, IGBT. Each device has its own device structure like this. It has own device structure. So based on the device structure, we apply this gate voltage, and these kind of things are happening automatically, and then the current flow occurs. So now we are talking about the device physics, right? I told you each device has a different name, and the device different names are based on the device physics or device structure. Okay, so now I think I have completed again about the P devices. In these P devices, you should be able to understand in all the P devices what is the common principle and why we have so many different devices, because it's based on the different structure of the devices. We get seen one example, that is IGBT. How can we make the current conduction by applying the gate voltage? So please try to read this topic by yourself in the textbook. Otherwise, you will not really remember any detail afterwards.